I'm Anil Kumar sharing with you a test question on higher order derivatives. The question here is position of an object is defined by the function s of t equals to t cube minus 12t square plus 36t, where t is measured in seconds and s in meters. You need to find the velocity and acceleration at any time t. What does zero velocity signify? Interpret zero acceleration, meaning of zero acceleration, sketch related graphs, and after sketching you need to find all these things. That is, determine the interval for decreasing displacement, decreasing velocity, decreasing acceleration, and slowing down. So that becomes a very important question from test point of view. To begin with, velocity is derivative of displacement and acceleration is derivative of velocity. So we have two orders of derivatives in this particular question. You can always pause the video, answer, and then look into my suggestions. So while solving this, I might take 2 pages. So that's the second page where I'll sketch the function and then answer the question related to intervals for decreasing displacement, decreasing velocity, decreasing acceleration, and slowing down. Meanwhile, you can always pause the video, answer this question, and then look into my suggestions. However, I'll begin with this portion where we have a graph already, and we'll try to understand how to analyze a graph and then understand the relation between the first derivative and second derivative. Okay, so for now we'll begin with the graph itself. The graph here is shown. We have A, B, and C. 3 graphs are shown here. The question for you now is, consider the given graph for S of t, V of t, and A of t. That means displacement, velocity, and acceleration. Identify the following intervals. But before that, we have to identify each curve and then answer these questions. So the questions here are, when is object stationary? When is object moving away? Find the interval for slowing down. Okay, so let's begin from here and then we'll get back to the main question. Now, this is one of the most important part of higher order derivatives, and derivatives where the application is related to velocity and acceleration. So the first part is that we have 3 different graphs given to us. How do we identify which one is for displacement, which one is for velocity, and which one is for acceleration? Correct. Now the key to figure this out is that whenever you have a turning point, maybe like this or maybe like this, then what is the slope at the turning point? That is the key. So whenever we have a turning point, the slope is always 0. Perfect. So derivatives will have that kind of a slope on the function itself, right? So let's look into this bold graph here, which is B for us. If I draw a tangent line here, what do I notice? This function is derivative, definitely, of b, and that function should have 0 at this place. That means we are looking for a 0 here. Now, we have a turning point there also. So there also, we expect 0 on the derivative, right? So that means that graph A is derivative of graph B, right? So we know from here that graph A is basically equal to derivative of graph B. Now let's look into the graph A. In graph A, we notice that we have one turning point, which is right there, right, at 4. Corresponding to this, we do have a 0 on graph C. That means that graph C is derivative of graph E. Now in these relations, we know very clearly that acceleration is derivative of velocity and velocity is derivative of displacement. So from this sequence, we can very easily say that graph B represents displacement, correct? Graph A represents derivative of displacement, which is velocity, and graph C, which is a straight line, represents acceleration. I hope this point is absolutely clear, correct? Now, this type of concept of sketching horizontal line as a tangent to the curve and finding corresponding zero in the next graph works for every curve when we are looking for derivatives. Is that clear, right? So the key is locate turning points and related zeros on the derivative. Is that clear? So that is key in arranging graphs by their derivatives. Is that clear to you? Correct? Now this was a much simpler question than you might get in your test problem, right? You could have even solved like this, that you have a cubic function, correct? You have a quadratic function and a linear function. And from there clearly we know that the derivatives order changes by 1, less 1 for a polynomial, correct? So in this case, cubic function will be displacement, quadratic will be velocity, and linear will be acceleration. So this one was very simple. But however, I hope you understand the technique, right? Now, we have done part A, which is identify each curve. Let's go to part B. When is object stationary? Now, whenever there is a question saying when is object stationary, we are looking for velocity equals to 0. Is it okay? At that point, the object is stationary. So if you look into the velocity curve, which is this one for us, it is stationary at 2 points when the velocity is 0. So it is stationary at t equals to 0 and at t equals to 6. Perfect. Part C. When is object moving away? So moving away means displacement is increasing, correct? So we observe that in this portion it is increasing, correct? And this portion also it is increasing. And therefore, answer for this is from 0 to 2, and which you can write as union after 6, right? After 6. Let's say 6 to infinity. D. Find the interval for slowing down. Now this is very critical. When will the object slow down? Condition for slowing down is that the product of velocity and acceleration should be less than 0, negative. That means opposite signs. Do you see that? So let us look into these graphs once again. We have positive velocity here and negative acceleration. So this is slow down from here to here. In this portion, velocity becomes negative, acceleration is also negative. So their product will be positive. So here it will speed up. Now, in this portion from 4 to 6, it is again slow down since acceleration becomes positive and velocity is still negative. Is it okay? So we have two intervals here. One interval is from 0 to 2 and the other one is from 4 to 6 when the object is slowing down. Perfect. So that is how we can answer these questions from the graph. I hope you find it very important and useful. Feel free to share your comments and views. And now let's get back to the equations we were working with and algebraically find all the solutions. Now let me also share with you that except for these values here on the left, the rest of the graph is similar to what you expect for the given question. Okay, so instead of sketching a new graph, I'll get back to this one. Perfect. Okay, so let's see, and I hope you must have got right answers for the question we started with. I hope you got the answer for this question. Now here is my solution. The question was, position of an object is defined by the object s of t, of the function s of t equals to t cube minus 12t square plus 36t, where time is in seconds and displacement in meters. We need to find velocity and acceleration. As you know, velocity with respect to time as a function of time is rate of change of position, right? So let's find derivative of the position function itself, which is applying the power rule, 3t squared, and that becomes minus 24t, and then you can factor, plus 36, correct. So that becomes the velocity. You could actually factor this. Let me write it in factored form. It really helps. So if I factor out 3, I get t squared minus 8t plus 12. Now 12 is 6 times 2, and we can easily factor this one also, writing this as 3 times t minus 6 times t minus 2. The factored form can give us zeros. That's the whole idea. So that becomes the final expression for velocity as a function of time in factored form, and this is in standard form. Now we'll use standard form to find derivative for acceleration. So acceleration, which is derivative of time, can be now written as 3 times 2 is 6, so we have 6t minus 24, derivative of a constant, as you know, is 0. So we can take 6 common, t minus 4. This step is very important. Factored form gives you zeros, helps you to make sketches. Standard form is easy to differentiate, right? So let's move on. Find velocity and acceleration at time t, so that is what we have. Now, what does zero velocity signify? So zero velocity means the object is not moving. Perfect. So that means not moving. Stationary. Is it okay? Now in our case, we have 0 at t equals to 2 and at 6, which is at t equals to 2 and at 6, correct? Part C is interpret zero acceleration meaning. Okay, so at t equals to 4, we know that acceleration, that means a of 4 is 0. It really means that the object is neither speeding nor slowing down. So it is constant speed, right? So that means constant speed or velocity. Is it okay? Not speeding, nor slowing down. Perfect. Now we have sketch related graphs, determine intervals. So this part we are going to do in the next page. So I hope with this you have understood basics about how to find velocity and acceleration given the displacement function. Perfect. You can add some more question here which can help you to sketch a better graph, is that you can find what is the velocity at time. We know at time 2 it is this, but you could say 3, acceleration as 3, and at this point is the object speeding or slowing down. So you could check that as one of your questions. I'll add few more questions here for you to do, and that is calculate distance traveled by the object in first 10 seconds, right? So that becomes a very critical question which you can try answering from the given information, right? So now let's move on to the part where we'll discuss how to sketch the graph, right? Now we will try to understand how to sketch graph from the given function. Here the function is S of t equals to t cube minus 12t square plus 36t. Now, displacement, let me write down all the equations, which is t cube minus 12t square plus 36t. For velocity, which is derivative of displacement, we got 3t square minus 24t plus 36, which could also be written as 3 times t minus 6 times t minus 2, which we did in the first part. For finding acceleration, let's find derivative of velocity, which is 6t minus 24, and that could be written as 6 is common factor, t minus 4, correct? So we get all these derivatives. You should also take care of units. When we talk about displacement, then the units are in meters, velocity is meters per second, acceleration in meters per second square, right? This is very important. So what I will do here is kind of sketch them in one particular graph overlapping. However, you should understand, since the units are different, right? So the values on the y-axis are definitely going to be different, perfect? They're not same, so don't get confused with this scale. I'm only overlapping since we have common time here. Is it okay? So we have common time, and I'll sketch a relevant graph so that we have some meaningful result for all this. So we are looking for a time period, let's say we'll go up to 8. Okay, so let's say this is 8 for us. Half of 8 is 4 for us. So let me write here 8, this is 4 for us, and that becomes 2, and that becomes 6. I've actually taken a very simple equation to work with. Now to begin with, let's sketch the cubic function s of t. This should also be written in factored form for sketching. Let me do it now. So let me do it now here. So s of t, we could take t common, right? So we have t square minus 12t plus 36, and that is 6 times, right? So that could be written as t times t minus, this should be t, okay, t minus 6. T minus 6 whole square. So let me rewrite this. I could write this as t times t minus 6 whole square. So as I said, all these equations are very simple to sketch. So as far as displacement goes, we have two zeros here, one to start with, the other one is at 6. So it's a good idea to find some values in between. So I'm not finding any values here in between since I'm not really labeling my y-axis, right? Just keeping safe. So I'm drawing this displacement in that color. So basically it's a cubic function, and this 0 is of order 2. As you know, polynomials, it will go like this. Is it okay? So basically we could draw a graph which will be something like this, coming down on that curve and then kind of going away. Perfect. So that becomes the displacement function. Now let us sketch the parabola for the quadratic function which is represented by velocity. So now I'll do velocity. I'm not taking any values. However, you should make table of values and sketch more accurate graphs. We have two zeros here. One is at 2, the other one is at 6. It's a parabola which opens upwards. If I write 0 here, I get 36, so I do have one value. Anyway, so what I'll do here is I'll just draw a parabola kind of going like this, right? And like this. Okay. So that becomes the velocity graph. Is it okay? Now let us sketch the third graph, which is a linear function for us, and it is acceleration. So minus 24 will be somewhere here, and we have a slope which is positive 6. So it's okay. So we can sketch this curve kind of like this. Let us say like this, right? Okay. So here we are just assuming the t is greater than or equal to 0, as it is for most of the applications we deal with displacement, velocity, and acceleration. Perfect. So here we are with the third curve, acceleration. Whenever you work with polynomials, derivatives are 1 degree lower, cubic, quadratic, linear. That makes sense. Now let's answer all these questions. So we have done the first part, that is of sketching. Now we need to determine interval for decreasing displacement. Decreasing displacement, clearly, where is the distance decreasing? So this distance is decreasing from here to there, right? So we have our result here. Decreasing displacement is from 2 to 6, right? So we could write this as from 2 to 6. Perfect. Decreasing velocity. So if you look at this curve, velocity is high positive to start with, and it decreases up to this point, that graph, parabola. And after that it increases, so it is decreasing from 0 to 4. Now don't think that 2 to 6 is negative, that means it is decreasing. No, velocity is decreasing. That means the object may be going further away, but at a slower pace. Do you see the tangent slope is very high initially, and then it decreases all the way up to this point. Do you see? This is called point of inflection. Now we have decreasing acceleration. As you will notice, acceleration is actually increasing, so there is no interval, none. The last is slowing down. Now I want to really work on slowing down and speeding up. So when we say slow, then we really mean that the product of velocity and that of acceleration is less than 0. And when we say speed, speeding up, that means this product is positive. Now when we are interested in slowing down, we are looking for interval where both have negatives, opposite signs, right? So to begin with, velocity has positive, negative for acceleration. So in this interval, let me mark this interval now. Let me mark this interval where the sign is being changed. So these are the intervals where we see change of sign for velocity and acceleration. Perfect. So if you look at it, in the first interval, this interval, acceleration is negative, velocity is positive, so that is slow. Perfect. Now both are negative, so that means speeding, right? So let me write fast. I should write speeding actually. Okay. Now after this, acceleration becomes positive, velocity is still negative, so it is again slowing down. And after 6, it is speeding. Does it make sense to you? So that is how we get the relation between slowing down and speeding. Let me also give you a formula for knowing whether it is going away or approaching the original point. And there we look into displacement and velocity product, correct? So if it is positive, then it is away. And if displacement and velocity product is less than 0, then it means nearing, right? So approaching. Okay. So that is how you could actually analyze most of the situations. You must have noticed by now that this is the graph which we really started with, right? So with this exercise, getting back and forth with almost the same thing, I think you would have completely understood most of the examples which could be done based on displacement, velocity, and acceleration. One question can you answer? When does the object return to its initial position? So this is the question for you. When will object return to initial means starting, initial position? Is it okay? So whenever we use the word initial, it means starting position. That means t equals to 0. Is it okay? So that is the question for you. Feel free to answer, write in comments. I hope you liked this video, understood all the concepts which we talked about. If you like and subscribe, that'll be great. Thanks for watching and all the best.